So I hope my screen is visible now. Thank you to the jury for the award, and I'm honored to be here. I also wanted to really acknowledge for this everybody in the NCCR Digital Fabrication and my colleagues at the BRG that have been instrumental to this. In particular, my professor Philip Bloch, Tom van Mele, and Matthias Ripman. So just to very quickly, not because you don't know it, but you do, I did this work in the context of the Bloch Research Group, where there is really a marriage between architecture and structure. And this is, of course, through computational tools and methods that we develop to design and build more efficiently, keeping material economy in mind. So in that context, my work really tries to address the challenges that are associated with building complex concrete structures. At the core, core value of it is to apply efficiency in terms of material, cost, labor, and time, to address the problem of expensive material and inefficient formworks in construction that often that are heavy and often turn into a pile of waste when it comes to really special geometries. So to kind of address this problem, the proposition is to go into the direction of a flexible formwork system, so to move away from the traditional rigid formwork systems, and in this case use specifically 3D knitted textile formworks. That is because fabric is a lot lighter than wood. For example, it doesn't need much support, and it produces a lot less waste. In moving away from these kind of rigid formwork systems, we can really try to hope and make an impact. But the caveat here is that these types of systems also force us to think about the geometry that we want to build. The reasoning behind the textiles, so the 3D knits, is that contrary to other types of textiles, knits can be prefabricated and directly into 3D shapes. They can be designed to have specific local properties and integrated features. I think the best example of that for everybody to relate to is the shoes that you wear that have all of these that are done in this way. So the way the system works is we start with a design, and the idea is to produce a fitting 3D knitted textile to produce that. That textile is then tensioned into a rig using auxiliary parts. It is coated with a cement paste coating to then become initially rigid as a formwork. Now there are two, let's say, challenging parts. The first one would be to go from the design to the knitting itself. And that can be done in two steps. So first we, depending on how large the design itself is, we discretize that into smaller pieces and produce knitting patterns, which are instructions to be able to produce this textile for a machine. And then the second challenge is, once we have this textile, how do we go to the formwork itself? Now, for the first part, the machines that produce these textiles look something like this. They're industrial machines. And to really be able to go from not just making your shoes and t-shirts, what we needed to do is develop a computational pipeline that goes from a design to a instruction for the machines in an automated ways. So I developed this pipeline of algorithms and tools that can translate these any 3D given geometry such that commonly available CNC knitting machines can produce these intricate formworks that become the base for lightweight structures. So in this context, then the example is Nitcandela, which you've already heard from Shajay. We built in Mexico City together at the MUAC, at the Museum of Contemporary Art. This structure, which is an homage to Felix Candela in its shape as well, is what is special about it is that it is a waffle shell. meaning that if we look at the section of it, it has cavities, so it has stiffeners in two directions. And that brings a second challenge to the type of formwork that you want to make, so that you don't only have globally doubly curved geometry, but you also have a locally complex geometry. To build the shell, we started by building a frame. We tensioned the textile with a cable net, which was the main load-bearing part of the formwork, into this frame. Then inserted inflatables into pockets which were pre-existing in the textile, coated that on one side with a very thin cement paste specifically designed to be used in this context by our colleagues at the Physical Chemistry of Building Materials in ETH. Once that hardened, the concrete can be applied normally, so the way you would do it with structures today. And once that hardened, the frame could be taken away and the balloons could be deflated, but the textile stayed in place. So that is also what you see on the inside of the pavilion itself, the concrete on the outside and the textile on the inside. Now, what is special about this is that the textile had two faces. It fulfilled an aesthetic role on the one hand and a technical role on the other, where the technical side had channels and openings so that we can introduce all of the cable net and inflatables and so on. These types of textiles are produced in one piece. This is one of the strengths of using knitting. Here's just an example of the front face and the back face that are very different, but they were produced in one go. Now, of course, the pavilion is too big to fit on on the machine itself. So we took advantage of the fact that with that machine, which is kind of a giant plotter, you could go in a fixed width, but for an infinite length. So we split the geometry into 4 pieces, resulting only in 4 seams overall. And those pieces were quite long. Some of them were quite long. For each one of those pieces, this pattern to instruct the machine was generated with the pipeline that I talked about earlier. And that was fed to the machine that then produced these 4 pieces of textile that are arguably maybe the largest scarf in the world at the moment. We took those, we packed them and put them in our suitcases, taking them to Mexico City. You can see Lex, my colleague that does the cement paste coating there. Once we arrived on site, we put all of these 4 pieces together. The seamstress that did this in 2 afternoons was probably very happy not to have to work on wedding dresses for once. And with having inserted all of the cables into that textile, what we did is we took it outside. Here you can see us fixing the nodes temporarily. We took it outside, put it around the center pole of the frame and hoisted the entire package up. Now, we did this very carefully, but that cable net and textile weighed only 55 kilos. We were just being incredibly careful with it for the first time. And once it was finally up, we could take a breath of relief that it did stretch to the size that we wanted. Now, what we also did with the textile and the cable net is to have specific edge detailing so that we could know till where the concrete goes. And then here you can see the balloons being inserted into these pockets of the textile. After all of these balloons were inserted, what we did is we coated the textile on one side, as I mentioned before, with a very special cement paste. And what resulted is this kind of Swiss chocolate type of formwork. And what I wanted to point out here and remind you of is that these protrusions that were done with the balloons are what make the cavities in the concrete structure at the end. And what is also specifically interesting in a sort of digital fabrication context is that usually we say now that machines don't care if they produce 500 times the same square or 500 times a different square. The thing that this does now is introduce a problem of logistics. So in this case, of knowing where to put each different piece and make sure that it ends up where it should be. In this case, that labeling question was taken care of through the textiles. So there is an intelligence in the system in that sense as well. Onto that formwork, incredibly skilled, incredibly, sure, I'll be done in a minute. Incredibly skilled concrete workers made sure that the structure could be applied. You can see them here doing this very skillfully. So finally, at the end, we got to this beautiful structure that has a hard concrete outside and a soft textile inside. The takeaways from this, and this is the last thing that I wanted to point out, are that we had a system where the textile was, and the cable net, so excluding the frame, were only 2,250 euros. It weighed 25 kilos. It was easily transportable. It was incredibly fast to produce. So we produced the 50 square meters in 36 hours, which would take otherwise 750, which is kind of equivalent to the 3.5 months that we needed for the project from the first meeting to the structure standing there. So in conclusion, by taking a simple logical idea, programming a machine to generate 3D geometries and scaling that up to a construction scale, this kind of work has the outlook to really make an impact in changing the way we build structures and have efficiency throughout the entire design to production chain. And what's more, those machines exist in factories all over the world. It's not just one. So we could also just send them the instructions. So thank you very much.